problem. So let's consider a cylinder. And there's many objects out there in the world that are cylinders. Okay, so you can think of soup cans, soda cans, all things like that. All right, and let's pretend we know it has to be able to hold a certain amount of stuff. Okay, so let's say I want the volume of this thing to be, I don't know, 15 inches cubed. And the question is, how do I build a can that's a cylindrical in shape that will hold this amount of stuff and use the minimum amount of material to do that? Okay? So that's our goal. So optimal today means we want to minimize a quantity. All right. Well, ideally, we think about yesterday, or think about the open-top box problem, we created a function for the volume of the box, we graphed it, and we found the minimum value it could have. Or the maximum value it could have, I'm sorry. We want to do the same thing here. We need a formula for the amount of material that's being used. So we need to think about how we make a cylinder. And if you think about a cylinder for a minute, well, it's got a circular bottom and a circular top, right? So we have two circles. And then also, we've got the side. I don't know if you ever thought about this, but the cylinder, you imagine cutting down the side like this and folding out flat, you actually end up with a rectangle. So this picture, it sort of represents the material I'm going to need to use. I need to know the area of these things, because that area sort of represents the amount of material I'm going to need to make this. All right, so let's make some variables here. We're going to say that the cylinder has radius r and has a height of h. Okay, and I claim that that's enough to at least start getting the formula. So I'm going to call this formula surface area, or SA. And the surface area is going to be the area of those two circles. Well, the area of each circle is pi r squared. So it's going to be 2 pi r squared in my surface area formula, plus the area of the rectangle. Well, that's a little trickier. I think we can see this much, that this vertical distance here, or this distance here, is just h. It's the height of the cylinder. So we know to find the area, it's going to be base times height. Problem is we don't know what the base is yet. We know the height is going to be h. But we claim, you think about that base of that rectangle, that green rectangle, we fold it around into a cylinder. There's a relationship between that base and some part of the circular top and bottom. The key realization is that the circumference of the circle is really the base of that rectangle. This base down here is this circumference up here. Okay, we know how to get circumference. It's just 2 pi r. So there you go. You got a formula for surface area. And I would say, wow, that would be great if I could just graph that and find a minimum for it. The problem is, though, is that if you look at it, here's SA. So this is like my y variable. Okay? And I know my graph, what I'd like it to be is I'd like it to have SA as my vertical variable. But along the x-axis, all right, I need to decide what's going to be my variable. I have r. Okay, so maybe I'll make this the r-axis. There's an r over here. Sure, no problem. And then h comes along. And you go, uh-oh, what am I going to do about that? I got to get rid of that h. Okay? And usually, in optimization problems, the way to do that is to use some kind of information that's been given to you to figure out h. Okay? In other words, we should be able to rewrite h in terms of r. And the key is to use the fact you were given. So we were given that the volume is 15 inches cubed. And you may or may not know this, but the volume of a cylinder is pi r squared h. Formula from your past. All right, so what do we know? We know that 15 equals pi r squared h. So what we can do is take that formula and solve it for h. And if we do that, we get h equals 15 divided by pi r squared. All right? And you can see what's going to be good about this, because if I replace h with 15 over pi r squared, then the h variable is eliminated from my equation. And now I can graph it, because it only has one variable. So keep that in mind. That's a goal with these problems. You want to get something as a function of just one variable. Right now, surface area is a function of the variable r and the variable h. So that's a function of two variables. And we're not going to graph things in 3 dimensions. So what do we say here? We say SA, surface area, equals 2 pi r squared plus 2 pi r times 15 over pi r squared. And we're really happy about this because now we have a formula that's all in terms of one variable. All right, it's advisable to simplify a little bit when possible. So I'm going to get rid of the pi's. I'm going to get rid of one of those r's. And now we get surface area equals 2 pi r squared plus 30 over r. Okay, so there you go. That's a formula. We can graph that thing, and we can find out where it's minimal. Let's go to our calculator for a minute here. We're going to graph that function. So we've got to open up the calculator. So here we are in our calculator here. We're going to go to y equals, get rid of the function that's there, and we're going to type in that new function. Now, just in case we forgot it, there it is, 2 pi r squared plus 30 divided by r. So 2 pi x squared, x is going to act like r here, plus 30 divided by x. Oops, that's 330. Hold on, I got to get rid of one of those 3's there. Delete, enter. There we go. Now, I'm not really sure about a window. It's sort of fun. If I can see the window over here, it actually looks pretty good. But let's see what window I have here. So my window is from 0 to 4.25. Okay, that's from yesterday. And then my y min is 0. My y max is 100. So we'll leave it like that for now and see what we think. Press graph, and you can see, look at that. You clearly have a graph that has a minimum value somewhere. And this is what we were hoping for. We were hoping for a minimum value. So we'd use the least amount of material, or have the least amount of surface area. All right, we can calculate the min if you do second calculate, and you go to number 3, minimum. It's going to ask for a left bound. On a T89, it'll say lower bound, but lower means left. So move to the left of where the minimum is occurring. All right, so there you go. I think that's good. Hit enter one time. Right bound or upper bound, it might say. Move over to the right of where the min is occurring. Hit enter one time. And then it's asking for a guess. So I guess I'll just go over here. I'll hit enter. And there you go. So we have a minimum when x is equal to 1.336. And then the y of 33.669 is really what the minimum surface area would be at that point. So the minimum surface area possible for this thing is 33.67 inches squared. And it happens when the radius is equal to 1.337. So if the radius is equal to 1.337, we end up with minimum surface area. Okay, let's just go back to this cylinder for a minute and see what this ends up looking like. So we know our radius is 1.337. And let's just take a minute and think about the height. Well, what would the height have to be? Well, think about it. We had a formula over here. We knew that the height was equal to 15 divided by pi times the radius squared. So we know that the height is 15 over pi times 1.337 squared. So we've got to figure out what that turns out to be. We'll type that in. Second quit. Now, this is worth typing in. You just be careful when you do this. You do 15 divided by, open parenthesis, pi times 1.337 squared, close parenthesis. Okay? So notice I took the time to put the denominator in parentheses here. I'm showing you that because if you don't, you do not get the same answer. 15 divided by pi times 1.337 squared. Okay? So you have to be careful of this. Some people think multiplication always happens first in order of operations, and then division second. Not really true. What happens is multiplication division always gets completed before any addition and subtraction, given there's no parentheses. But if it's just multiplication and division, and you write an expression like this here, then it goes just from left to right. That's actually the proper procedure. You just proceed from left to right there, and that's it. Okay? In the upper expression, I told the calculator I want you to multiply those things first and then divide it into 15. Okay. So that's that. So the h turns out to be, actually I just forgot what the answer was. So the h turns out to be 2.67. That's what h was, 2.67. So that's sort of interesting. I say, well, what number is that? Well, I'm just going to go back for a minute. I'm going to take this number, 1.337. Actually, I won't do it. I'll just tell you. If you take the number 1.337 and you double it, you actually get this number of 2.67. That's what happens. Sort of a fun fact. So the diameter of this thing is 2.67, just like the height of it is 2.67. Okay? Sometimes referred to as the square right circular cylinder. Square meaning that its diameter and its height are the same. Now, if you think about most soda cans you've seen in your life or picked up, or soup cans, it is not the case that their height and their diameter are the same. So it means most of these cans are built in such a way that they're using a little more material than they need to.